We are ready to continue with our goal to build proteins up from simple levels of structure to the more complex. So far, all we've done is string amino acids together with primary structure, that is, with peptide bonds. And we're ready to move on and look at more three-dimensional type structure. I'm going to show you a structure of a protein. I like to show examples of what we're working toward. This is a larger and more complex protein than we've seen before. This happens to be an enzyme from the virus that causes COVID-19. This is an enzyme whose job it is to mature proteins, and it's necessary for the life cycle of COVID-19, and therefore it's a major target for drug development. When we look at a protein like this, we see things we've seen before. Notice we've got these curlicues, these spirals. In this case, they're purple. We also have things that are arrows that kind of parallel with each other. They tend to be more like this or crosshatched. And we also see simple, thin, less regular structures. These are all elements of what we call secondary structure, and that's where we want to go next. So let's consider that secondary structure is regular repeating patterns of main chain hydrogen bonding. And what we said before is that this is kind of like the walls and columns when we build a house. We're going to use these types of motifs to build proteins instead of houses. Let's go on to our first element of secondary structure. Let's make a note that we are talking about secondary structure. 2-0, that's secondary. And what we want to talk about first is alpha helix. I want to warn you right away that the alpha in alpha helix has nothing to do with the alpha carbon that we talked about in amino acids. We're going to use these Greek letters over and over again, and they don't always mean the same thing. Alpha helix means simply this was the first type of secondary structure that was discovered in proteins. Now, let's move on to this type of representation. This looks a lot different than what we've seen before. It's a stick structure, and what it is going to be sticks that represent peptide bonds, and the nodes where these sticks meet are going to be the alpha carbons. So let's take care of the alpha carbons first. Everywhere I draw a red line here, or a red dot, is going to be an alpha carbon. And, I won't do them all, but you get the point. And then everything in between those two red dots on the stick is actually the peptide bond that connects those two alpha carbons. So let's finish off one of those peptide bonds and show you, there's the peptide bond right there. And these 6 atoms that we have shown here, the 2 red alpha carbons and then the 4 atoms that compose the peptide bond, they are planar, they're flat, and they don't have a lot of mobility. So that's why we can draw it as a stick. We would see the same thing down here. I'm going to draw it in a little bit, squeeze it in there. That is going to be another peptide bond. Notice they're going in the same direction. It looks a little crunched because we're looking a little more end-on to that particular stick or that peptide bond. Now, if we take all of these peptide bonds, and remember what we have here can be described not only as a peptide bond, but beautiful acceptors. These carbonyls are beautiful hydrogen bond acceptors and great donors with these NHs. If we coil these up over and over again into a spiral, or what we call a helix, what happens is we have the ability to create perfect or very nice hydrogen bonds. Let's show that dot, dot, dot there. And I'm also going to do what I did earlier with hydrogen bonds. I'm going to circle those and show you the 3 atoms. Remember, we have 2 electronegative elements, and they share 1 hydrogen unequally between them. That's a really nice hydrogen bond there. Now that is a great, strong, straight hydrogen bond. And remember, hydrogen bonds themselves are kind of weak. However, we can do this over and over again. Every carbonyl can interact with an NH above it. Every NH can interact with a carbonyl below it. And we can just end up, I won't draw all the atoms, but we can end up with an enormous number of hydrogen bonds. And in fact, every NH and every carbonyl is going to be stabilizing the opposite in a hydrogen bond, except out here on the ends. For instance, we would have a carbonyl out here that is unpaired and an NH down here that is unpaired. Those are not going to be paired. But we end up with a large number of fairly weak bonds, and all together these form a beautiful, strong, and very rigid column. So this alpha helix is straight and it's going to be strong, and this is in a sense like a column that would hold up a building. So a couple of things that we need to talk about. First of all, this is a right-handed helix. When I say that, I only mean that the helical nature of this is kind of like a normal wood screw. If we were to screw this into a wall, we would be righty-tighty, kind of lefty-loosey, like we would with a regular screw. It has chirality. The mirror image would be a left-handed screw sense. It's always a right-handed helix in alpha helices. The other thing we can say is that this is a really important one, is that there are 3.6 amino acid residues per turn of the helix. So what exactly do I mean by that? Well, every helix has a certain tightness or looseness to it, and what we can do is we can start with any particular residue that we want. Let's go ahead and take this residue right here, this alpha carbon. Now, if we start here, it's pointing out kind of right at us. If we then proceed to the next alpha carbon, that's 1, then 2, and then 3rd right here. Now if we go to 4, we've gone past where we were when we started down here. But let's do it again. 1, 2, 3, and then about 3.6 of the way over for this last one is going to put us right above. And that is a non-integer helical turn, 3.6, or roughly 3.5 amino acids per turn. I'm going to go ahead and write that one down because that is definitely worth remembering. We're going to be using it in later videos. Let's just write down this other thing as well. This is strong. We've already said it, but let's write it down. Strong because of many main chain hydrogen bonds. Remember we said secondary structures held together by main chain H bonds. Okay, that shows us what the alpha helix is, and in order to bridge to the next video, I want to point out that we haven't talked at all about side chains. All we're showing you is the peptide bonds, the alpha carbons. Where are the side chains? Well, there's no room for them in between the levels of the helix. There's no room inside the helix. The only place we have left for them is to be coming out from the helix like that, outside the helix, coating the outside. We'll pick that up in the next video.